Hi, this is Karen O'Brien with FLO 2D Software, and as a follow-up for the April 9th, 2024 ASDSO Tailings Dam Webinar given by Jim O'Brien, I am going to supplement his webinar with some project development and mapping videos. First video should cover the project overview and some of the data resources for doing tailings dam failure projects, and the second video will cover mapping the results. So let's start with the project overview. This is the Brumadinho, Brazil filtered stack collapse that occurred around January 25th of 2019. So what happened in this, let's see, here is a pre-disaster aerial to show the dam site before it happened. This was taken from Google Earth. Historic view, and this filtered stack of tailings collapsed on January 25th, and approximately 77 to 79% of this tailings material was mobilized, liquefied, and then flowed downstream. So we are going to show you some of the ways that you can set models up like this and model and map them as a dam breach model. Okay, so that is the overview of the project. You can get information about the project report. Just search online to get the project failure report. It's a pretty extensive report, and it's in both English and Portuguese. Let me make sure and move this over to my other screen just so that I don't forget anything on this. So let's talk data resources. So in order to set up a project like this, you need to start with your coordinate system. So in this case, I used this coordinate system that says EPSG 29101, but I don't know if that's the correct coordinate system used in Brazil. It's just one that worked for me, and it worked so that I could get all my data into this coordinate system, reproject all of my polygons and rasters, and then load them into QGIS so that I could use them for project development. And then we need some elevation data. So in this case, I used an elevation pre-disaster raster. You don't typically get really good elevation data for these types of models unless the mine happens to give you some of their data. They have really great data that they use to study the growth rates and production rates of all these areas. So they have good elevation data, but they probably aren't going to share it with you. Sometimes you can get elevation data from the government and they will share it with you for your project development, but a lot of us simply go the free route because it's easier than fighting for that other data. So in that case, you can use a plugin called Open Topography DEM Downloader. And you'll need an API key for this, but you don't have to pay for it. You just go to their website and you get an API key, and then you can download these different kinds of data. Sorry, my API key is somewhere else. I got to go find it and reload it. But you have your standard SRTM 30-meter data. In this case, I think I used the Copernicus data, which is a digital surface model, not a DEM, so that might be, that means like some buildings and things might be in there. Or you can use the NASA DEM. Now, I'm just going to tell you right now, if you use the NASA DEM from today, it's going to include some of those downstream mitigation features. If you go to the NASA or ASTER DEM website, you might be able to get the data from shortly after the event, and that would be excellent data if you want to do some kind of calibration modeling, because it includes all the scour and the collapsed bridges and railroad grades and things like that are all in that post-failure DEM. But I didn't go get that. Instead, I used this Copernicus data because it seemed to be fairly decent representation of what's out there pre-failure. And that is this data right here. And then we modified this data with a couple of tools that I'm not going to cover how to use these tools. That's part of the class, so I won't cover it here. But we modified this data with some shape files so that it looked more like removing the tailings ponded area. In this case, of course, it was filtered stacks, but for the class we kind of use it in many different ways, but the bottom line is we remove the volume of the fail event, and then we get this modified elevation raster. In addition to that, you might also want to get, so this was a Google Earth history, probably a screen capture or an export, and then loaded onto QGIS. And then QGIS has some graphic management tools that can allow you to pin this to the correct location of the map using a couple of points, like a waypoint type thing, and then it will like scale it and align it to your map correctly. And also it'll geo-reference it so you can use it in other mapping software. Or you can do the Google satellite, which will be usually pretty modern data, and this just goes straight to the Google server and gets the most up-to-date modern map. There's probably a plugin out there that does historical Google map or Google images. I have not seen it, or my guess is you can also just directly go to their server and maybe tag a date or something to get some historical data using this search QMS. You can probably do that. I've never done it. You can also add any other kind of data that you want using this metadata search tool here, where you can search metadata that's free and available online, and that data can be imported into your map. And of course there's also some layer management where you can, let's see if we can add a layer from, you can get ArcGIS RST servers, you can get WMS servers, you can get all kinds of data servers to add data to your map. And it's very easy to connect to those as long as you know the email or the URL of that data server. And of course, if that data server is protected by a login ID and password, you also need that too. Let's see, so that covers elevation. And this Google satellite comes from a Quick Map Services, so it's a plugin that you install, and then once you install it you need to go to settings and you need to add additional maps to it. And these are the three that I most commonly use, so I hide all the other maps. Then let's see, that takes care of aerials, elevation. Let's talk land use and infiltration data. In here I have, whoops, that's not the right one. I have a land use shapefile, and this is basically a rasterized land use data that would be a combination of soil and land use. And what we've done with it is we have, let me open the attribute table, we have modified it with an N value column where we estimate an N value for these different types of land use, and a curve number column where we have used some of the soil properties, upper horizon soil properties, and land use imperviousness to create a curve number for this data. And again, all of this is in the class, so I'm not going to go over how we developed these parameters because it's part of the class, and it just takes too long. We also have buildings, and I have two sets of buildings that I just downloaded into, but this would be the buildings that are down in this area, and then these would be the buildings that I used in the class. And you can get these buildings from a tool called OpenStreetMap Downloader. So I'm going to show you that quickly. And OpenStreetMap Downloader is again another plugin, and you click on it and then you select your area that you want to download and put that to a safe location. I'm just going to call it OSM and load and click OK, and that is going on to the OpenStreetMap servers and is downloading their data as polylines, points, and polygons. So, and let me, sorry, I didn't mean to, that should have all been added to this alternate group. So let me get that into the right spot real quick, and then we'll turn off that satellite image so we can see it. So this is your OpenStreetMap data vectorized. Now, your typical OpenStreetMap data, it comes down more as a raster. So if you see your Quick Map Services and you load your OpenStreetMap standard map, let me pop that out of there so we can see it. This would be the OpenStreetMap standard mapping. They're very good in Brazil, not so good in other countries, maybe like Ecuador, but it's a raster, so it's not very handy. It's not very useful to you. So let's just remove it, and instead you get this vectorized data where let me turn that back on, where the points represent parks and locations that are important. The polylines represent roadways, and the polygons represent all kinds of things, but you can export this data and save it as a shapefile, and then you can modify that shapefile and you can filter out things like buildings and delete all the things that are not buildings, and then that becomes a layer that looks like this or this. Okay, I'm going to remove that map. Let's see, that takes care of buildings, aerials. Okay, let's talk hydrology for a minute. So there is a lesson that tells you how to import, plot, and connect to all of the rainfall gauges in the area. Let me open this up a bit. So along these mountain ranges, or I guess they might just be foothills, whatever they are, there are rain gauges in this area that collect rainfall data, and they have a specific timing record. So you can download that data and you can start to I would say just analyze that data to get maximum daily rainfalls, and then you can project those out into that Hirschfield PMP, which is kind of the standard method for developing a rainfall data for your simulation. So with that, you get, in this case, we estimated 422 millimeters total rainfall for the PMP and assigned it to a rainfall distribution curve. So I'm going to select that curve to show you that the data for this rainfall distribution curve is time in hours on the left and percent total in, that's the percent total of the storm as a uniform rainfall event. So every cell gets 422 millimeters of rainfall distributed as a percent of the total using this curve. And I'm going to turn that off because we only simulated rainfall for one of the events. We didn't simulate it for the final event. And then you can use that either to estimate the rainfall in your project area, using the watershed that is above your site, or you can do a larger area and then you can use it to estimate the rainfall for all of these different dam sites on here, so that you could do more of those dam sites than just, of course, the one that has the data. Okay, that is hydrology. Then infiltration, and the infiltration data comes from, again, from this land use shapefile. Oh, I don't know if I showed this or not, but yeah, I did. Okay, yeah, we open that and you see that the SCSN, and that land use data comes from a plugin called, a couple of different plugins. Probably you're going to need some soil data, you're going to need some land use data, but this is the source of the land use data. It's called Map Biomas Collection, and this is a really sweet server that is set up for all of South America and Central America, and you can get the land use data, and of course it can change over time. I think they use this to study deforestation and mining practices in Brazil, and you can download this and convert it into vectorize it and use it to develop your end value data and your curve number data. Of course, you'd have to use it in conjunction with a soils layer too. And again, that's in the hydrology lesson, so I'm just going to skip the rest of that. So let me just remove that data because we don't want it in there at this time. And that covers everything. So that was data resources for coordinate system, hydrology, infiltration, elevation, aerials, buildings, and tailings dam parameters I did not cover. So let's take a quick look at the class. And of course, if you've already seen Jim's webinar, you understand some of the parameters that are used for modeling and mapping tailings dam failure. And so what we do in the class is we first show you how to set up your computer, and in that lesson you will set up QGIS and install your FLO2D plugin. And then we show you how to start your project. So this talks about how to load your elevation data and how to set your coordinate system. And then we go on with the hydrology lesson, which is your rainfall and infiltration data. Then we add boundary conditions, which are let me open up the user layer so you can see the boundary conditions, which we apply a downstream boundary on the end of the project that sets up a normal depth discharge for the downstream boundary. Whoops, sorry, I clicked the wrong button there. Then we go, well, the channel model's on a different project, so we do channel modeling, but that's on a different project because the channel in this area is really just a series of retention basins, so it's not really channel modeling. Then we use the first real breach lesson is to use the tailings dam tool to define a breach hydrograph using different mud flow parameters. So once we set that up, we use an inflow hydrograph to represent the breach. That is defined on a specific point on the map, and we define that on this map that has the pre-failure condition, and the inflow hydrograph just initiates and the water flows out of that node and in the downstream direction as a breach release event. Then you see here that the results for that would be tailings dam tool, and we'll talk about those in, oops, sorry, I didn't mean to click that. We'll talk about those when we get to mapping. But you essentially get a tailings dam hydrograph using the known geometry of the map and the volumes of the event and the estimated volume of the release. Of course, any tailings dam scenario could have any given number of estimated release volumes, and that's all well documented in many different journals, and so you can use those papers to estimate a release volume, and that's what the tailing dam does. It applies those the estimates from those different papers and calculates a release event, including things like the mud flow concentration or the sediment concentration of the tailings material, and the total release volume, and then it converts that into a breach hydrograph. So what we can do with that breach hydrograph is we can apply mud flow parameters to that. Now, if you're lucky, or if you have a good lab and good relationship, you can get some of that tailings material and you can conduct laboratory studies and develop the viscosity and yield stress parameters for your event. But if you're not able to get that data, you can use one of the menu relationships that we have here in the plugin. And of course, we typically start with Glenwood 4, and in this case I also used Aspen Minefill. So these are just two different rheology studies from different events in Colorado, and those events were used to develop these coefficient and exponent of the viscosity and yield stress for those different soil types. And of course, if you're doing just a tailings dam tool, you're just doing a mud debris flow model. If you're doing a sediment transport, because you're trying to model two-phase, then you can also apply the more standard rheology parameters for the sediment transport. So you can do one or both, one, the other, or both. And in this class, we show you how to set both of those up. Let's see, what else do we have here? We have, that would do their tailings dam parameters. And once you have all that data, you can then start to model these different events. So there are many different ways that tailings dams can fail. So we try to show you the 4 different ways that we can set up this particular event. So obviously this is only one of those different events. This is only a static stack failure. So that is one of the ways that you can model this event, but there's different kinds of tailings dams. For example, this one is static stack failure, but this one over here is more like a quintessential tailings dam where it has a water surface on top all the time, and it's probably a slurry, and so there's definitely a difference in like the final concentration of the mud that's in here or the tailings that are in here, and different parameters that you would model that with. So in this case, we show you how to set up these different events, but we always use this same fill because we know the volume of this event. So we can set it up with the tailings dam tool, which is just a breach hydrograph that you put somewhere in here, or we can set it up with a levee and reservoir volume that you can just collapse the whole levee, or you can set it up with a point where you set the breach event to grow laterally across the levee at a given, it's not a given, it's a predicted rate of failure. Or you can set it up as a stack collapse, and if you set it up with the parameters of really high compacted final concentration of material, then maybe only a portion of it would collapse, and that's also a common way to set these up. So we try to show you how to set up these, and then in the class we also do like a cascading failure and things like that. Of course, we have to pretend there's another dam down here that this one can cascade into. So we have all those different scenarios that you can model and test. Now so that's kind of it for project setup, and that kind of finishes out this first video. So I'm going to pause or stop the video, and then I'm going to pick it back up in video number 2, and we'll talk about mapping results. So I'll go ahead and finish this one here.